Okay, so we are in Introduction to Statistical Learning. Do I have a picture of the book? I guess I don't. Okay, Introduction to Statistical Learning, Chapter 6. And we're in the conceptual questions. We're on question 7. And in the book, this one kind of has an indicator that it's a little bit tough. And, it's not bad. So, so here's what we're doing. So we're going to derive a connection between Bayesianism as well as these two methods that we've learned here, the lasso and ridge regression. Okay. Now, this connection is interesting, but I don't really know that it's all that surprising. And I just want to start by saying why might it not be surprising? Okay. So remember that the lasso and ridge regression are both trying to put some kind of constraint over the beta coefficients. Okay, well, Bayesianism is doing a very similar thing. It is constraining the solution space with a prior distribution. Okay, and so the fact that we can translate one type of restriction, or we'll just call it a restriction, between Bayesianism and ridge regression and lasso really shouldn't be all that surprising. So, but nevertheless, let's push on here. All right, so we have several parts, and I think that parts B and C rhyme with parts D and E. Part B and C will deal with lasso, and part D and E will be basically the same questions, but in reference to ridge regression. But first, part A, well, I'll just scroll down here. So what are we doing in part A? So we're supposed to suppose that y, our outcome, can be expressed like this. Okay, so just a linear function with a error term. Okay, so this is just an intercept and then a bunch of predictor variables and corresponding beta coefficients. And then the error term, where all of the error terms are independent and identically distributed, normal distribution with a mean 0 and standard deviation, or I'm sorry, a variance of sigma squared. Okay, and we're meant to write out the likelihood. All right, so remember that a likelihood is a statement about the probability of data given a specified set of parameter values. Okay, and here our parameters are beta and sigma squared. Okay, so the likelihood, here is for each observation, it's the product of all the probabilities for each of the observations. It's something like this, right? It's the probability of the data given the parameters. And here, we're told that our data is normally distributed, and so now all these probabilities are normal distributions, which can be written like this, where from here on out, I'm going for mu, or for this big expression here, instead of rewriting this every time, I'm just going to write mu, but it represents this. Okay. So this, this is our likelihood, but we can simplify this a little bit so that it looks like this right here, right? Because so if I have, so this is a constant, and so I can just take it outside of this and multiply it, or raise it to multiply it by itself n times. Okay, and then with the exponent, I can just simply add each, add this term for, add that term for each observation, and I get kind of this simplified version of it. But anyway, okay. So now that we have our likelihood, now we get into thinking a little bit about lasso. Okay, so what we're going to do is we're going to assume that our betas are all independently and identically distributed as a double exponential distribution with a mean 0 and a common scale parameter of b. Okay, so that means that the probability of a beta, or its probability distribution, is this guy right here. Okay. And so now we're supposed to write out the posterior for beta in this setting. All right. So now remember that the posterior in Bayesianism might look something like this right here. Okay. So the posterior for our parameters would be the likelihood, which we already derived, times the prior. Okay, and so here we have a prior for the betas, and I'll talk about the sigma squared in a second, but it looks like this, and then it's divided by this normalizing constant here. Oh, you know what? That should actually have another term here. I will fix that. But it's divided by a normalizing constant, which is basically the sum or integral of all possible values in the numerator. But it needs a corresponding prior here in the bottom. So let me fix that here. Okay, so everything fixed. Now this question is only asking about beta terms. Okay, and we're assuming that beta and sigma squared are independent of one another. And so I'm just going to simplify all of that. So I'm going to simplify all of that by dropping the sigma squared terms. Okay, and so I have this guy. And now notice that, like I said, this denominator is just a normalizing constant, and so I'm just going to be working with the proportional expression, which is just the numerator. Okay, so the posterior is going to be proportional to the numerator. All right. Again, the reason that I'm doing this is because the denominator is a constant, and so we could always put it in at some other point. Having it in there kind of complicates the calculations, and it's also not necessary to do what we need to do here in this problem. Okay, so so now we know what the posterior looks like in generic terms, and so now we need to find the expressions for our problem for these two guys right here. Okay, well, what is this? Well, this is just the likelihood, and we've already found that. We found that in part A. Okay, so that's more or less represented here, I think. Okay, and then the probability of the betas. Well, we're given that here, and so that's given here. Okay, and we can do some simplification until we. Well, okay, so I'm just going to assume you can follow the simplifications to this point. And now notice that we have these two constants out here, which I will now call k. But because we're working with proportionalities, k being a constant, I'm just going to drop it and say that, again, our posterior is proportional to that expression right there. All right? Okay, so now here in part C, we are meant to argue that the Lasso estimate is the mode for beta under this posterior, the one that we just derived, under, that guy right there. Okay, so what does this mean? We need to show that the estimate that we would get for beta under Lasso estimation would be basically this right here. Okay, that was a weird way to say it. This represents an entire distribution that has one value that is the peak of that distribution, and that is known as the mode, and we want to show that the mode of this is the Lasso estimate. Okay, so how do we go about doing that? So the way that we're going to do that is we're going to look for first we're going to take the loss function of Lasso, which is this, and we are meant to minimize that. Okay, and we're just going to set it equal to the maximum of the posterior distribution. Okay, now the maximum of the posterior distribution is also the maximum of the expression that we just derived. Remember, we didn't derive the posterior necessarily, we derived something that the posterior distribution is proportional to. But the thing that it's proportional to, well, the maximum of the thing that it's proportional to is going to be the maximum of the of the posterior distribution. Okay, so I'm setting, again, the loss function or the minimum of the loss function of Lasso to the maximum, which is again the mode of the expression that we just derived, which again is proportional to the posterior distribution of for when beta has a double exponential distribution. Okay, now I'm going to do a little bit more here, which is I'm going to get rid of this exponential here because it turns out that the maximum of this expression is also going to be the maximum, or I'm sorry, the beta that maximizes this expression is going to be the same beta that maximizes the log of this expression. Oh, geez. Okay, and so if I take the log of this, then that gets rid of the exponential. Okay, so now I have my Lasso loss here is equal to this. Again, I'm setting them equal to one another, and we're going to just see what shakes out. Okay. Well, now the maximum of this, if I just reverse the signs, is the minimum of the same expression, but now with the signs reversed. Okay. And then I'm just going to do one other trick here to make them look similar, which is I'm going to take this 1 over 2 sigma squared, and I'm going to pull it outside into these parentheses. Okay. So I'm going to distribute it over both of these terms. Okay, when I distribute it here, I just get this back. But when I distribute it to the second term, I get something weird. Okay, well, not weird, but that is not equal to that. So I need to account for that. I need to cancel out the fact that I'm going to have a 2 sigma squared over here. So I put it in the denominator. So I put 1 in the numerator, and so now when I multiply that through, I get back the same expression here. Okay, and so now look at this expression and this expression right here. Okay, look at the parallels between them. All right, they look very, very similar. Okay, one thing that's different is this 1 over 2 sigma squared, but that's a constant, and so that's not going to affect the minimum value, so I can get rid of that. Okay, and now notice that the only difference between this expression and this expression is here we have a lambda, and here we have 2 sigma squared over b. So if lambda equals 2 sigma squared over b, well then the Lasso expression is the mode of the posterior distribution when beta has a prior distribution of the double exponential. Okay, so I hope you followed all that. All right. Okay, so now we're moving on to D, and D is similar to part B, but instead of dealing with Lasso, we're now dealing with ridge regression. Okay, so now so the steps are very, very similar, but now our prior for the beta is a normal distribution, not a double exponential. Okay, and so you go through the same steps here, and I won't belabor the point, but we come out with an expression like this right here. Okay, again, where the posterior distribution with this prior for the betas is proportional to this expression here. Okay. Notice that C here represents the variance for the distribution for the betas. Whereas this variance has a square in it, this one does not, and so but they're both variances. Okay. So now in part E here, we're supposed to show that the ridge regression estimate is the mean and the mode for beta under the posterior distribution that we just found. Okay, and so because we've already done this for Lasso, I won't go through every step, but again, what we're doing is we're setting the minimum of the loss function for ridge regression equal to the maximum of the posterior distribution that we just derived. Okay, and then we can quickly by reversing the negative signs for the posterior distribution, we can compare 2 minimums. Okay, this and this, and we find very quickly that the minimum of the loss expression for ridge regression looks very, very similar. This is the final expression. Looks very, very similar to the mode and to the mode of the posterior distribution. Okay, so we have this. Okay, so this is just this first expression and the last expression. okay, to show how similar they are. And so we notice that if lambda equals sigma squared over c, then the two expressions are equivalent. Okay, and so what we have found is that the ridge regression estimate for the betas is equal to the mode, the most probable value for the posterior distribution when beta has, you know, the normal prior, okay, when lambda equals sigma squared over c. All right. Now we're meant to show that under that we have both the mode and the mean, and what we've really found is the mode, right? We found the most probable value in the posterior distribution, but for symmetric distributions like the normal distribution, the most probable value is the mean as well, right? So the mean is the mode, okay? And so by finding the mode, we've also found the mean here. Okay. All right. I guess that's it.